Hello everybody, today we will learn about chapter 1. This is our class about cryptography. So what I'm going to talk about today is introduction to cryptography. Let's start our interesting course from now on. Okay, so what we're going to do today is the content of this chapter. In this chapter, what we're going to learn is overview on the field of cryptology. Then I will talk about basics of symmetric cryptography, cryptanalysis. Then I will talk about some historical ciphers, substitution cipher. Then I will talk about modular arithmetics, Cipher cipher, affine cipher, and some recall about hexadecimal and ASCII notation. Okay, let's start with overview on the field of cryptology. What do we doing actually? So before I will start this, I have to talk about the classification of the field of cryptology. So cryptology itself divided to the, so let me just use cryptology divided to the two part, cryptography and cryptanalysis. Cryptography itself divided to the three part, symmetric cipher or symmetric cryptography, asymmetric cryptography or cipher, and protocols. Symmetric cipher itself divided to the two parts, block ciphers and the stream ciphers. And chapter 5, until chapter 5 we will learn about symmetric ciphers. Then we will start chapter 6, we will compare the symmetric and asymmetric cryptography, but we never mention about protocols. Cryptanalysis, we will talk about this in this chapter. So what is that? Okay, let's start our cryptology right now. So now some basic facts. Ancient cryptography, yes. So early signs of encryption in Egypt, for example, in before our area start 2000 years ago, yes, BC, they were encrypting by letter-based encryption schemes. Yes, this is like the Cipher cipher, popular ever since. So affine cipher or substitution cipher, which we will talk in this class, in this chapter. Then symmetric ciphers. What is difference of the symmetric ciphers and asymmetric ciphers, which I will talk about soon? Symmetric cipher, all encryption schemes from the ancient time until 1976 were always used the symmetric ciphers. Starting 1976, we start using asymmetric ciphers, yes, or we can say that it is public key cryptography or asymmetric cryptography. Was openly proposed. This was openly proposed by Diffie, Hellman, and Merkle. Also, we used hybrid scheme. What is hybrid scheme? Hybrid scheme is the majority of today's protocols are hybrid scheme. What is that? It is both of them, symmetric cipher and asymmetric cipher, used at the same time. In one protocol we are using symmetric and asymmetric cryptography. So for example, for symmetric cipher, we can do the encryption or message authentication, and asymmetric ciphers we can use the key exchange or digital signature. If you don't understand it, and that's completely fine, because this is overview of whole our course about it, yes. So this is like big idea what we're going to do, but eventually you should be fine. Actually, you should understand it better. Okay, now this was about the summary what we're going to do in the course. Let's talk about basics of symmetric cryptography. So symmetric cryptography, so what is the different name of the symmetric cryptography? We can say that symmetric cryptography, or we can say that private key cryptography, or single key cryptography, or secret key cryptography. It's up to you. Now, what is the idea? What is the problem statement over here? We have two parties, yes, Alice and Bob. And Alice, what Alice would like, this is Alice is good and Bob is also good. They would like to communicate with each other. Now Alice would like to send her message X to Bob. We are in unsecure channel. We are internet or something like that. When I say unsecure, it means that Oscar is sitting and listening that, yes. So Alice would like to send this message X to Bob. We are unsecure channel, yes. Alice and Bob would like to communicate via an unsecure channel. And a malicious third party, Oscar, bad guy, has channel access but shouldn't be able to understand the communication. We have to make sure that when the Oscar sees the message, he shouldn't understand what is there written. So what does Alice have to do in here? Who comes to the help? Cryptography comes to the help. In here, Alice has to encrypt the message. The encrypted message becomes the ciphertext and send the ciphertext via insecure channel. And Bob will decrypt the message. From the decryption, he will learn the plain text. Now let me explain to you the idea. The solution in here is encryption with symmetric cipher. Oscar obtains only ciphertext Y that looks like a random number. So what happened in here, Alice, before sending the X, what she will do is she will encrypt the message. For the encryption, actually, she needs the plain text and she needs the key. Yes, she needs the key. She will encrypt the message with the key K and generate actually the ciphertext. And where the ciphertext is seen by the bad guy Oscar, and it has to be as a black box which is not able to be understandable. Yes, and notice that in order to do the decryption, Bob has to have exactly the same key for symmetric cryptography, exactly the same key. For he will get the ciphertext. He will get the ciphertext inside of the decryption. Sorry. Inside of the decryption, he will get the ciphertext with the also the involves the key. Then he generate the X. Yes. So now the question is, how do they? We have to make sure that this key has to be send it via secure channel, because if Oscar would know what is the key is, he can easily decrypt that and get the information about the plain text. Okay, now let me just talk about little bit of vocabulary, which we're going to talk a lot in this class. So X is the plain text. This is like a message of the Alice, like social security of, you can think about something very private of the Alice, social security or something like that. Y is the ciphertext. What is ciphertext? Ciphertext, it is the black box which is seen by the Oscar. Yes, and the key K is the key which is used for encryption and decryption. And we need to have a key space. What is the key space? So Oscar now tried to break it. In order to break it, he needs to have the number of keys by using brute force, for example. Which keys can be possible to do the encryption and decryption? This key 1, key 2, up to key n. This is called key space. Okay, now symmetric cryptography, where we're going to do the encryption equation is Y is equals to EKX. Decryption equation is DKY. We can rewrite it that way. This is differently saying that we are thinking as a function. Function is getting an input X, encrypting with the key K, and generating the ciphertext. This is the Alice this is Alice work, yes? Alice generates the ciphertext. Then she sends this ciphertext to Bob. Bob will use exactly the same key, uses the ciphertext. Everybody knows the ciphertext, and using this function, he will get back the Bob will get back the plain text. Yes, this is the Bob's work. Encryption and decryption are inverse operation if the same key is used on both sides. Yes, because why? What does it mean? Inverse function. Yes, so it means that f of g of x has to be x. Yes, so if you look to the decryption, dk of y is equals to, what is your y? Y is equivalent to this one, because this is coming from this is coming from here. Y is equals to we just plug it, but since the decryption has to be equivalent to x, that means that this two function has to be cancelled. That means that encryption and decryption are inverse of each other. Important thing is over here, the key must be transmitted via a secure channel between an Alice and Bob. Why? If it would be sent via insecure channel, you see, if the key, this is the ciphertext, and the key would be sent over here, Oscar would learn about it, then he is going to do exactly the same decryption, and he will get the plain text back. So this shouldn't be over here. The key has to be sent via secure channel. Okay, now the secure channel can be realized as by manual installing the key for the Wi-Fi protection or human cursor. For example, the Alice and Bob would like to use, they wouldn't like to communicate. They can say before they are a part of each other, they can share their keys. They can say that we will use this key in future our communication, and key doesn't change it so frequently, but the encryption and decryption actually changes most frequently. Secure channel, however, the system is only secure if an attacker doesn't learn the key. I'm repeating this several times, yes? So what happened in here, the problem of secure communication is reduced to secure transmission and the storage of the key. So now let me summarize what I tried to explain it right now. The board explanation, yes? Let's recall one more time what I tried to explain you earlier. So I'm going to use blue color maybe. We have two parties, Alice and Bob, yes? Bob. Alice would like to send the message X. She has the message X, but she cannot just send her X via insecure channel, because over here the bad guy is sitting, the Oscar, and Oscar may learn about those informations. So what she has to do before sending the X, she will encrypt it. Before the encryption, she would need the key also, and then she is going to generate the ciphertext, yes? Then this ciphertext is going to the via insecure channel. Eventually Bob got the ciphertext. What he will do is, it's like a black box. He doesn't understand. It's like blah 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 blah. So Bob will use the decryption algorithm, but in order to do the decryption, he would need exact the same key for symmetric cryptography to do the decryption. So with the input of Y and key of the algorithm D, he got actually X back. Yes, so and I have to make sure that this key has to be sent via secure channel. This is the key has to be sent via secure channel. Yes, so and as soon as this can be the human cursor, or asymmetric cryptography also can help us to transmit the key exchange. So we will talk about this more, but key has to be sent via insecure channel. So now I explained to you what is the problem of secure communication. Yes, problem of let me talk about that. I'm going to use different color right now. The problem of, let me say that the problem was big. Yes, the problem was what? Problem was problem of secure communication. Secure communication. Decrease it, becomes smaller to another little problem. Secure transmission. Secure transmission. And storage of the key. And the storage of the key. Yes, so this big problem reduce it to smaller problem. So differently saying, what is smaller problem? How can you generate this secure channel? Differently saying, how can you send this key, secure create this secure channel, and how can you store this key so that nobody would learn that? So this was what I was trying to explain it, and I try to wrote down on the board in here. Now another question is, should we make encryption and decryption functions secure or public, secret or public? So differently saying, we have this function encryption, yes, and this function is decryption. Should we make this encryption function, sorry, I mean that this encryption function and decryption function is secret or public? Secret or public? You can pause and you can think about it a little bit. What do you think about it? Yeah, of course I will answer to it in right now, but what do you think about it? Before I will answer to that question, I have to start about cryptanalysis. What is cryptanalysis? So if we're going to go to the trees, let me go back to the trees right now. Yes, which I show. Cryptology divided to the cryptography and cryptanalysis. Cryptography teaches us how to construct the cipher. Yes, now you understand what is cipher. And the second part is cryptanalysis, how to break that cipher. Yes, so this is what it teaches the cryptanalysis. Cryptography, how to construct it, the cipher, and the cryptanalysis, how to break the cipher. So now let's go back to this section of cryptanalysis. Why do we need cryptanalysis? Let's talk about that. There is no mathematical proof of security for any practical cipher. So differently saying that if somebody gives you, this is encryption is secure, I can prove it mathematically. We cannot prove it actually. Yes, their only way to have assurance that cipher is secure is to try to break it. Differently saying that if you never try to break it, you don't know that this is secure or not. We cannot prove it via the mathematical proof. So the most important principle in our course is Kirchhoff's principle. it is the most important in modern cryptography. Yes, what does it say? A crypto system should be secure even if attacker knows all details about system with the exception of the secret key. What does this Kirchhoff's principle says to us? Kirchhoff's principle says to us that this is the, let's say that this is our encryption and decryption algorithm. The Oscar has to know how that algorithm is constructed. That's fine. That's what it says. Except knowledge of the key. Yes, of course, knowledge of the plain text, because this is what we are hiding for. Yes, so now let's go back to that one. Yes, in order to achieve Kirchhoff's principle in practice, only use widely known cipher that have been cryptanalyzed for several years by good cryptoanalyzers. Differently saying, we cannot just use the cipher whatever we created a couple days ago, or like by ourselves, and we never shared. We have to share to everybody and wait until this was broken or not broken, test it. If it is tested thoroughly, then we can use it for the secure cipher as a secure cryptography. Yes, encryption and decryption. So in order to answer to this question, what do you think? Should we make encryption and decryption function secret or public? Do you understand? Of course it has to be public. Why? Because it has to be used by Kirchhoff's principle. Why? Because there is no mathematical proof that the cipher is secure. So what do we have to make sure? That we have to rely to the public, so that public can try to break it. If it is not breakable, then we're going to use it. So I hope it is understandable. Yes, and of course, intuitively you always would like to hide everything. Differently saying, you don't want to share. In cryptography, historically, nobody wanted to share anything. Historically, it is tempting to assume that cipher is more secure if its details are kept secret. However, history has shown time and again secret cipher can almost always been broken once they have reverse engineered. For example, we had content scrambling system, CSS, for DVD content protection. We were hiding all the information over there. By reverse engineering, they cracked that one very easily. So what is the idea of the Kirchhoff's principle? That give to everybody to try to break it. If it is not breakable, then use it. Yes, this is the big idea of Kirchhoff's principle, and this is super important actually principle for our course. So now let's go to the cryptanalysis, attacking crypto system. Cryptanalysis itself divided to the three parts: classical cryptanalysis, implementation attack, and social engineering. Classical cryptanalysis itself divided to the two parts: mathematical analysis and brute force attack. So when they try to break the algorithm, first of all, they try to break it via mathematics. Yes, if it doesn't work, they can try to do it by brute force. What is brute force? By trying to do breaking by all possible actually keys. Another one is another part of cryptanalysis, implementation attacks. What is implementation attack? Implementation attack, it's like reverse engineering. For example, we have a card, debit card or credit card. Yes, so what we're going to do is we try to from the eBay, if somebody would like to attack it, they will buy something like when we going to swipe, but the encryption and decryption happening over there. Yes, so somebody, the Oscar, could buy some kind of the monitor where it says that it's like ATM machine. You put it inside of the like in this kind of monitor, you will say that this is ATM machine encrypted. While it's going to encrypt, it leaks some information about the key. So this kind of idea about implementation attack. But if our card is not properly secure from the implementation attack, then it can be easily be cracked. Yes. So implementation attack, you can understand that like trying to implement it or reverse engineer it and get the information from that. Yes, so this is another branch of cryptanalysis, breaking the cipher. Another one is the most easiest one, is the social engineering. What is the social engineering? It's before I will go ahead, implementation attack try to extract the key through reverse engineer or power measurement for the banking smart cards. Yes, social engineering, it's like tricking a user into giving up her password. For example, somebody is calling saying that I am from Social Security office, can you please give me this information, getting information from you, and the cheating it. Yes, they're differently saying. If you have time, try to watch this link. This is very interesting link about social engineering. It's very interesting. You can see that. Okay, now let me go back one more time. What is cryptology? Yes, I'm gonna make it bigger, the bigger chart in here. Cryptology itself divided to the two parts. Yes, cryptography and cryptanalysis. Cryptography, what is cryptography? Cryptography is making a cipher. Yes, and cryptanalysis, they are trying to break the cipher. Yes, there is two part of different kind of the cryptographist. For example, I am cryptographist, so I try to make the cipher. Another part of the people they look to my cipher, they try to break that one. Yes, and cryptography itself divided to the three parts: symmetric cipher, asymmetric cipher, and protocol. In this class we learn about the symmetric and asymmetric cipher. When I say symmetric cipher, it means that the keys Alice and Bob you are using for the encryption and decryption exactly the same thing. When I talk about asymmetric cipher, the keys Alice and Bob are using exactly different keys. So they are not exactly the same. We're going to have public key and private key. And in this class we will learn about symmetric cipher and asymmetric ciphers. When we learn about the symmetric ciphers, we will divide this one to the two parts: block cipher, which is encrypting blocks, and stream cipher, encryption bit by bit, which I will talk in detail. This one is chapter 2, and this one is chapter 3 and 4. I will give an example. Yes, so now cryptanalysis itself, we divided to the three part: classical cryptanalysis, implementation attacks, and social engineering. Classical cryptanalysis is classical. They're trying to crack the cipher via mathematically or brute forcing. Brute forcing, it means that using every possible keys, or using the branch is implementation attack. I try to explain by doing reverse engineering. Yes, and social engineering. It's by tricking the people and getting their information. So let's go back to the brute force attack. What is brute force attack? It is an exhaustive, you can call this one as exhaustive key search against symmetric ciphers. Yes, so we treats the cipher as the block. You remember this? What we were doing actually? Let me just you remember that when we were doing the encryption and decryption, we are doing decryption, let's say, yes, we decrypting the ciphertext. So just a moment. In order to do the brute force attack, the Oscar has to know what Oscar has to know. Oscar has to know about x0 and y0. Yes, requires at least one pair. He needs to know at least one pair of this one. After, I don't know how he got this ciphertext corresponding the plain text. This is plain text. This is ciphertext. Yes, ciphertext corresponding how did they get it? But let's say that Oscar knows this x0 and y0. If he knows that, he knows the key space. Yes, what he tried to do is he knows how the decryption works, because by Kirchhoff's principle nothing will be secret other than the key. And what will happen is he will try to use each key. For example, let's say we have key space is key 1, key 2, up to key n. Yes, so what will happen is he knows what is x0, what is y0. So the Oscar will take the first key, and he says that if I will take this ciphertext and I will decrypt it with this first key, am I going to get this x0? If it doesn't take, if it is not true, what will he do is he will use another key. So it didn't work, for example, he will use second key. If it didn't work, he will use third key. If it didn't work, it will go until it will exhaust all the keys. So this is what it means, brute force attack. Yes, or the exhaustive key search. Now question is, how many keys do we need in here to make sure that this kind of brute force attack wouldn't be possible? So if we are saying that we have 64 bits, what does mean 64 bits? Let me talk about that. Bits, it means you can have either, it's like box, you get 0 or 1, box 0 or 1, yes, and box 0 or 1, yes. And how many possibilities? Let's say that we have 64 for this box. We have 2 possibilities. In here we have 2 possibilities. In here we have 2 possibilities. If we have 64 bits, that means we have 2 to the power of 64. The key space is, it's going to be 2 to the power of 64. So I hope it's understandable. If we have key size is 64 bits, this is called short term. Short term. It can be cracked within few days or less. So it's not good enough to have that one actually. Usually we would like to have at least 128 bits. If it is 128 bits, our key size, it's going to be 2 to the power of 128. It's long enough. And this is long term. It takes several decades in the absence of the quantum computer. If we don't have a quantum computer, using our computer, it will take us several decades, several years to crack one decryption without interrupting, if we're going to run this brute force attack. If we're going to have 256 bits, the key space, it's going to be 2 to the power of 256 bits, so we're going to have long term. Even though we have a quantum computer, it is resistant to that also. So 256, it's going to be top secure. Yes, important thing is to note is an adversary only needs to succeed with one attack. Yes, thus a long key space doesn't help if attacks social engineering or some kind of attack exists. So differently saying, if there is a more efficient attack available, it's not necessarily that if brute force attack doesn't work, then there is no other attacks. There may be other attacks. We will see it in this lecture, in this chapter, differently saying. Okay, so I talked about the big idea about cryptanalysis. Now, the next step is I would like to talk about substitution cipher. So let's go to the historical ciphers. Yes, first thing is the substitution cipher. It is a great tool to understand what is the brute force attack and what is analytical attacks. Yes, encrypts letter rather than bits. So in here, historical ciphers usually they encrypt the letters. But nowadays we encrypt the message bit by bit, this is it, or block by block. So it is like all ciphers until and after World War II. The idea is we're going to replace each plain text letter by a fixed other letter. For example, we're going to have a letter A. We can choose any letter other than any letter, actually, differently saying, you can choose from the alphabet any letter for the letter A. So for example, we choose for the cipher text is K, and for, let's say that plain text is B right now. Yes, and we can choose in here the choosing for the letter A, choosing any letter, is there is 26 possibilities. I can choose anything because we have 26 letters. Yes, for the letter B we have how many possibilities? If I already choose K, how many letters I'm left with? So I'm going to have 25 possibilities, and I choose D in here. Yes, for the letter C I have 24 possibilities, so in here I choose W, and it goes through. So on the last letter I don't have a choice, I will choose whatever is left. Yes, so now we have, for example, we would like to encrypt the message ABBA, ABBA. Yes, so how would you do that one? A, it means K. Yes, K. B, it is D. K, D, D, K. So encryption becomes K, D, D, K. Now let's say that we have a cipher text is given for us this. Yes, this is the cipher text. Can you read it? So our goal is to make it some kind of attack and try to read this message. Yes, and this is this substitution cipher. How, now question is, do you think that substitution cipher is secure or not? How secure is the substitution cipher? Now let's look to that text before we will answer to that questions. So you can pause my video in here and think about yourself. Do you think it is the secure or not? I'm going to present two attacks in here. The first one is exhaustive key search. Exhaustive key search, which is brute force attack. In order to do the brute force attack, I need to have the key space. Yes, if I will do the brute force attack, I need to have a key space. Key space in here. Key space. So now, what is the key space? For the possibilities of the A, we said we have 26 possibilities. For the letter B, we have 25 possibilities. For letter C, we have 24 possibilities. It goes until 1. And this is how we call it. This is 26 factorial. Yes? If you're going to approximately calculate this, this means 2 to the power of 88. Yes? Now, the substitute, the key space is, let me call this one is key space. Key space is 26. But this is very large actually. It may take a couple years to break it if we're going to use it to crack the substitution cipher with using exhaustive key search. The search through 2 to the power of 88 keys is completely infeasible without today's computers. So earlier table on the key lengths, yes, so we noticed that the 64 bits, it's going to take short term, yes, but 88 and 128, it is between of that, it may take us a long time to crack that, yes. So now, okay, question is in here, can we now conclude that substitution cipher is secure since a brute force attack is not feasible? Absolutely no, because in order the cipher will be secure, it has to be resistant from all attacks. If it doesn't work for the brute force attack, it doesn't mean that it doesn't work for the other attacks. So no, we have to protect against all possible attacks. So now I'm going to introduce the second attack, which is letter frequency analysis. Another one, it's also brute force attack, but this is more analytical attack rather than just using brute force. So in here, letters have very different frequency in the English language. It depends what language they are using, but in English language we have actually very frequently the letters. Moreover, the frequency of the plain text letter is preserved in the cipher text. It is not going to be changed. For example, for the letter E, notice that, sorry, for the letter E, this letter, it's approximately, it almost takes 13% of all letters in a typical English textbook. We use E. Another second frequent letter is T. Yes, it's going to be approximately takes 9%, and so on. And I have a chart over here which letter is coming in what frequency. Yes. So for example, what you can do it's one of your homework, and how to solve that one, the substitution attack, you have a text. In that text you will code it and calculate how many letters do you have in the text. After you calculate that, you will say it how many letter A you have it and what is the percentage, how many letter B is in there and what is the percentage. After you got the percentage, you will say that you will think that you can change A with that number, you can change B with that letter, and so on. Yes, so this is how you will analyze it in your homework. So now let me show it in this example. The breaking the substitution cipher with letter frequency attack. Let's return to our example. You remember that we would like to break this text right now. Yes, this is the text. I calculated and I noticed that Q is coming the most frequently, and I know that Q is in English language is coming the most least actually. Yes, so I substituted, since Q is coming the most in here, I substituted with E. So this is capital letters, it's going to be our cipher text, the plain text, differently saying. Yes, then what we're going to do in here is we will continue searching for the next frequent letter, and we will substitute it by further guessing based on the frequency of the remaining letters. We obtain the plain text. So what did we get in here? We will meet in the middle of the library at noon. All arrangements are made. Okay, now so the breaking the substitution cipher with letter frequencies. In practice, not only frequencies of individual letter can be used for an attack, but also the frequency of letter pairs, differently saying that, for example, in English letters we have TH is coming the most, Z or THE is coming, or letter pairs or letter triples, we can work with them also. So what did I try to demonstrate in here? Important lesson is even though the substitution cipher has a sufficiently large key space, the key space was 2 to the power of 88, this is sufficiently large, it can easily defeated with analytical method, differently saying that if you cannot break it with brute force attack, it doesn't mean that you cannot break it. You have to try to attack it a different way. This is essential example that an encryption scam must withstand all types of the attacks. Yes. Now, what we're going to talk about right now is modular arithmetics. The modular arithmetics, I hope you learned about that, and I would highly suggest you to work on this modular arithmetics very highly, because we're going to use this modular arithmetics until end of the semester. Please study very well, listen it very well. Okay, short introduction to modular arithmetics. Why do we need to study modular arithmetics? It's extremely important for asymmetric cryptography, RSA, elliptic curve cryptography, and so on. So when we're going to learn about public key cryptography, they are so important. And also, historical ciphers can be elegantly described with modular arithmetics. We will learn about Caesar cipher, affine cipher. They are all relies on the modular arithmetics, which you will learn it later in this chapter. Okay, now what is the short introduction to modular arithmetic? Generally, most crypto systems are based on the set of numbers that are discrete. What does mean discrete? The set with integers are particularly useful, like set of integers, or finite values if we only compute with finitely many numbers. It looks like if it looks like abstract, let's look to the clock. In our clock, actually, we have only the numbers 1, 2 up to 12. Yes, we don't have number 25, for example. I cannot say to you that let's meet at 25 o'clock, because it doesn't make sense, because 25 is not in that set. So what it makes sense in here to say that I will meet you at 1 o'clock. Yes, something like that. What happens is after 12 it's going to be repeated again and again, and this is what it means modular arithmetics. That's what's happening in here. Short introduction to modular arithmetics. We develop now an arithmetic system which allows us to compute the infinite set of integer, like 12 integers. We have a clock from 1 to 12. That's what we're going to do right now. It's crucial to have an operation which keeps the number within the limits. We have a boundary. After addition and multiplication, they should never leave the set. For example, if we add, it has to be inside of this range. It doesn't go to 13, 14 or any number. It will be always in that set. So what is modular arithmetics? Let A, R, M, they are integers. Yes, and we are assuming M is positive number. Yes, we write down A is congruent to R modulo M. It means that this number R, if you subtract from the A, R subtract A, divisible by M. Yes, is divisible by M. Differently saying, M divides R minus A. M is called modulus and R is called remainder. If it looks like abstract, don't worry about it. I'm gonna bring an example so that it would be more understandable for you. So for example, we have 12 modulo 9. For example, A is 12, M is 9. So what will happen here? So you have 12 is going away from the 9. What you can do is you need some number. If you subtract that number, this is divisible by 9. Or another way, what you can do is you can take 12, divide by 9. You have how many exact 12s do you, how many 9 do you have in 12? You have only 1, and the remainder in here it's going to be 3, and this is what we are working, the remainder. Yes, we can write down the 3 as remainder over here. Or if you go to the definition, you can see that R minus 3 minus 12 is equals to negative 9. And negative 9 divides, is divisible by 9. You know that. Yes, this works. Another one is, let's do the 34 modulo 9. One way of doing that is 34 divided by 9. How many 9s do you have in 34? You have exactly 3 of them. If you multiply 9 times 3 is 27. Yes, so you're left with 7. Yes, so in here the remainder is, you can say it is 7. Yes, so another one, or you can say that 7 minus 34, this is equals to negative 27, and negative 27 is divisible by 9. Yes, that's also fine. Now let's work with the negative number. How would you handle this negative 7, for example? You cannot do that way as I showed you in here. In here, I would show you different thing. So I would say that negative 7, how many 9s do you need to make it positive integer? Positive integer, and it's the smallest positive integer. Yes, so is it enough to have 1? Yes, it is enough, because 9 minus 7, it's going to give me 2, and 2 is smallest positive integer in this case, because if I will have a 2 in here, I have 18 minus 7 is going to be 11. 11 is greater than 2. 2 is the smallest positive integer. I'm putting 2 over here. Yes, I can put it in definition. 2 minus 7 is going to be 9, and 9 is divisible by 9 itself. Yes, this is how you could continue doing the modular arithmetics, and I hope that you know about this and you learned this previously. If you didn't learn about this, please try to work on that. So the remainder is not unique. Yes, for example, 12 is congruent to the 3 modulo 9, because 3 minus 12 is divisible by 9, but also 12 is congruent to 21, because 21 minus 12 is also divisible by 9. Similarly, those things, yes, the differently saying remainder is not unique. But what we're going to do is, for the convention in cryptography, we're going to get the smallest positive integer. So which remainder do we choose? By convention, we usually agree on the smallest positive integer r as remainder. This integer can be computed as, I hope you remember that a can be q times m plus r, and r has to be greater than 0 or equals to 0, and less than or equals to m minus 1. For example, this is going 12 can be equivalent to 1 times 9 plus 3, and remainder is 3. This is the convention. So that differently saying, we would like to have 12 is congruent to the 3 modulo 9 rather than 21, -9. We need to make sure that this remainder has to be strictly less than 9, but it has to be greater or equivalent to 0. So the what we would like to have, this is the solution for the convention. Okay, now let's do some examples. Yes, so let's do some examples. If you would like to stop this video, go ahead, stop this video, and I will continue, and you can check it later. But let's do it together if you don't want to stop it. So 15 congruent to the 7. Yes, so what you can do in here is, first step is 15 divided by 7. How many 7s do you have in 15? You have 2 of them, yes? And the remainder is 1. Or you can rewrite this one as 15 is equals to 2 times 7, and the remainder is 1. And this is your solution. Either way is fine. And this is going to be the congruence over here. Similarly, you can write down 11 divided by 7. So you have exactly 1 7 over here, and the remainder is 4. Or you can rewrite this one as 11 is 1 times 7 plus 4, and this is the solution over here, has to be there because we are working with the remainder. Now let's work with -1. Yes, when you work with the negative value, you have to ask yourself, -1, how many 7s do you need to make it smallest positive integer? I think it's enough to have 1 of them. Yes, so this is going to be +6, so the answer is +6. But let's work with -11. How many 7s do you need to make the smallest positive integer? Do you think it's enough to have 1? I don't think so, because if you have the 1 over here, you're going to have over here -4. But I need smallest positive integer, so this is not good enough. So I need, I think, 2 of them, 2 7s. Yes, 14. 14 minus 7 is going to be 11. It's going to be 3. So this is going to be 3, and the answer is over here is 3. And similarly, actually, you're going to do it with -54. Yes, how many 7s do you need so that I'm going to get the smallest positive integer? So if I will have a 7 over here, 7 times 7 is 49. It's going to be still negative. Yes, but if I'm going to have 8 over here, 7 times 8 is 56. It's going to be positive integer, so which is going to be 2. So the answer in here is 2. I hope you understand how to work with the negative numbers. Now, how do you add to modular arithmetics? Yes, so 15 modulo 7 plus 11 modulo 7. Yes, let's work with each of them. 15 modulo 7, we just calculate that. This one was 1. Yes, and 11 modulo 7, you remember this was a 4. Yes, this is the 4. So this is 4. 1 plus 4 is 5. 5 modulo of 7 is again 5 because it is less than 7 and it's positive number. And 15 plus, but what is that asking you? 15 plus 11. Add them first. If you're going to add them, you have 26. Then you can reduce that. Yes, if you reduce that one, 26 divided by 7, how many 7s do you have? You have exactly 3 of them, because 21, 3 times 7 is 21, and remainder is 5, and this is what we wanted. Yes. Now notice that doing this way or doing that way is exactly the same thing. The answer is the same solution. So differently saying, what did I try to explain to you right now? The a modulo n plus b modulo n, and then taking modular arithmetics is equivalent to evaluating a plus b modulo n. Yes, so it doesn't matter. Similar thing with the subtraction. I'm going to use a different color. So 15 modulo 7, you know that this one was what? This was 1, yes, and this one was 11 was what? 11 modulo 7, it's going to be the 11 modulo 7, it was 4. 1 minus 4, it is equals to a negative 1 minus 4 is negative 3, but negative 3 is how many 7s do you need to make it positive value? Only one is good enough, so the answer is over here is 4, so I put the 4 over here. Another way is evaluating, just take 15, subtract 11, take 15 and subtract 11 without doing the modular arithmetic. You have a 4 over here, and then take modular arithmetic. So you're going to have a 4 modulo 7. Yes, so notice that this is exactly the same thing. So what I wanted to present, that a modulo n minus b modulo n, taking after that modulo n, is equivalent to this number. Similarly, actually, for the multiplication. So you have 15 modulo 7 is equivalent to what? We just calculate that. This is 1. 11 modulo 7 is equals to 4. 1 times 4 is 4, and done. Yes, but what is that asking? You multiply that. You have 15 times 11 is this is 165. Yes, then take reduce by modulo 7. If you divide by 7, 165 divided by 7, you have 23 of 7s, and the remainder is 4. So you see that evaluating this way or that way is exactly the same. Now, question to you, which way is much easier to evaluate? In my opinion, by reducing is much easier. You don't need any kind of calculator rather than multiplying first, then reducing. So you better reduce it before you do any kind of operation. Yes. So now I'm going to stop in here, because the next step is I teach you how to add, subtract, multiply in modular arithmetics. The next class I will start to talk about how can we divide it in modular arithmetics. I hope you enjoyed this lecture. Study hard. Thank you very much.